this is John Whitaker for the Mathematical Analysis 2 class, and this is our 25th video lecture. And today we want to conclude what we're doing out of Chapter 3, which has to do with series. And then we're going to move on into Chapter 7, which has to do with sequences of functions and types of convergence and properties having to deal with sequences of functions and how they converge and what qualities do they maintain. But first we want to go ahead and finish up Chapter 3. And you might remember we ended Lecture 24 with a fact having to do with if one of the series converges absolutely and the other series converges, then the product series will converge to the product of the series involved. I want to move to a statement, kind of the converse of what I just said, and that is this statement, or theorem, that says if the series the sum of the A sub n, the sum of the B sub n, and the sum of the C sub n's converge to A, B, and C, and C sub n is equal to, let me write it down here, A sub 0, B sub n plus A sub 1, B sub n minus 1 plus A sub 2, B sub n minus 2 plus A sub n, B sub naught. So this is the product series. Okay? Then C will have to be equal to A times B. I made a small mistake in the introduction of this lecture, and I said, here we're going to start with this fact that has to do with kind of the converse. It's not the converse of the statement that we ended with last time, but it is a statement that's related to those product series. So I'll let it stand on its own. We're not going to prove this. It's just kind of a statement that I wanted to get on the board for us to be aware of. The last topic that we're going to talk about in Chapter 3 has to do with rearrangements of series. And here's the definition. It says, we're going to let the sequence K sub n run from 1 to infinity, be a sequence in which every positive integer appears once and only once. That is, we can think of K sub n as a one-to-one function of the set of natural numbers onto the set of natural numbers. So that's what K sub n is. If we let A prime sub n be equal to A sub K sub n, and again, n runs from 1 to forever, then the sum of the A prime sub n's, n running from 1 to infinity, is called a rearrangement of S sub n. I'm sorry, of the sum is n runs from 1 to infinity of just A sub n. Do an example of that. So as example, we consider the series as n runs from 1 to infinity of minus 1 to n plus 1, 1 over n. Well, let's see, when n is equal to 1, that's just going to be 1 over 1, minus 1/2 is the next term, plus when n is equal to 2, what's this, 1, this was 2. This is when n is equal to 3, we're going to get 1/3, and it's minus 1/4, and so forth. Plus 1/5, goes on forever. Okay? Now this is a convergent, alternating series. A rearrangement of the series is, so I'm going to rewrite it as 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7. Then I'll have minus 1/4. Then we'll have plus 1/9 plus 1/11 and minus 1/6. And plus, it's going to keep going on in this fashion. So what we're having is from our regular series that's listed up here, our original series, we're taking two consecutive positive rearrangements so that we have the two consecutive positive terms followed by the previous negative and so forth. We're going on like this forever in terms of making the rearrangement. Now, if we let S equal to this sum, as n runs from 1 to infinity of minus 1 to the n plus 1 times 1 of n, which we know converges, okay? Then we look at this in a certain way. We can say that S is equal to 1 minus 1/2 plus 1/3, and then plus the sum as n runs from 4, or n runs from 1, if you will, up to infinity. So rewriting the terms, we would have minus 1 to the n over n plus 3. And that will give you the other terms that are listed up here. Add to these first. We write this in this way to gain a little information. Well, first of all, let us notice that each of the partial sums for this part of S, which is n running from 1 to infinity, of minus 1 to the n over n plus 3, is negative. And so that means that this sum, whatever it converges to, is negative. And it must be convergent because it's part of the convergence series. It's the tail end of the convergence series. So here's what we have. S, with the original sum or series converged to, has to be less than 1 minus 1/2 plus 1/3. And then it would be plus this part, I mean S would be this plus this series. But this series right here is negative, so this first part is going to be bigger than S. But that's equal to, just simple arithmetic, 5/6. So we know that S is less than 5/6. Now we're going to turn to the rearrangement. If we let S of n prime be the nth partial sum, let me write down the rearrangement. It was 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6 plus and so forth. And if we look at them and we do the following, these terms grouped in threes have the form (1 over 4k minus 3 plus 1 over 4k minus 1 minus 1 over 2k. That's what the terms look like, grouped in terms of 3 things at a time. So the thing to notice is that 1 over 4k minus 3 plus 1 over 4k minus 1 over 2k. That's going to be greater than 0. You can use algebra to show that. So here's what we have. We get the following. We get S prime sub 3 is going to be less than S prime sub 6, which is going to be less than S prime sub 9, and so forth. It's positive quantity. And so, the lim sup of S prime sub n, which we know will be greater than S prime sub 3, which is equal to 1 plus 1/3 minus 1/2, has to be, which is equal to 5/6. Lim sup. Of the S prime sub n's have to be greater than 5/6. So what we can say then, the rearrangement cannot converge to S equal to the sum, as I think the n runs from 1 to infinity, of minus 1 to n plus 1, all over n, the original series that we were looking at. What we're saying here is something that I alluded to at the beginning, I believe it was, of our last in-class meeting, and that is we're seeing an example where we're talking about infinite sum, and you get some result when you add them. But if you rearrange how you add them, because it's an infinite sum, you don't get the same as the original sum. You know, 2 plus 3 is the same thing as 3 plus 2. But if you have infinitely many terms and you rearrange them, you may not get the same answer when you sum them up. And so we'd like to know, well, when is it that you can rearrange them and get the same answer? And so I'm just going to write down a theorem that kind of illustrates the difficulty of how bizarre it is, if you will, in terms of doing rearrangements and what you can get as far as answers. And so here's a theorem. We won't prove it. This is the first one that indicates this kind of surprising nature of rearrangements. And then we're going to state a theorem and prove it, having to do with when you can rearrange a series and still get the same result no matter how you rearrange it. All right, here's the first result I want to list. Let the series of a sub n be a series of real numbers which converge but not absolutely. Okay. Suppose minus infinity is less than or equal to alpha is less than or equal to beta, which is less than or equal to infinity. Then there exists a rearrangement of a primes, sub n we'll say, so that's my rearrangement, with partial sums S sub n prime such that the limit goes to infinity of S prime sub n equals to alpha, and the lim sup of S sub n prime equals to beta. Again, this theorem is not going to be proven, but it's something that just really, in my opinion, is startling in terms of the kind of unexpected nature of a sum. You know, you can rearrange these terms and get anything that you want, provided it's not absolutely convergent. So let me write that out very carefully. So implications of this theorem are, one, if this sum of a sub n's converge, non-absolutely, okay, then given the number, we can find a rearrangement of this series that converges to this number, to the given number. So it's not that if you do a rearrangement, you're going to necessarily get another number. You can get any number you want by making the right rearrangement in terms of the answer of the sum. In this situation, where we have a convergent, where we have a convergent non-absolutely series of real numbers. And that's the first implication. And then, two, we can find a rearrangement that doesn't converge. Okay? For any series A sub n that converges non-absolutely. It's just kind of shocking. So you can come up with a rearrangement that won't converge even though the original series does converge. And you can do a rearrangement that will converge to any number you pick, even though the series converges, as long as it doesn't converge absolutely. Well, here's the theorem that says all rearrangements will be the same as the original, and it has to do with absolute convergence. So here it says, if the sum of A sub n is a series of complex numbers which converge absolutely, then every rearrangement of this series converges to the same number, the same sum. And we're going to prove this. Okay, so here's the proof. We let this sum of the A primes of n's, which equals to the sum of A sub k sub n, be a rearrangement of the series of A sub n's with, for a rearrangement, partial sums. Here's the partial sums for the rearrangement. S of n prime. Okay. here's something to note. Given epsilon greater than 0, given any positive number, there exists an integer, really it's a natural number, n, such that for all n and m greater than or equal to n, we have that the sum, the absolute value of the sum of the absolute values of the a sub I, as I runs from m up to n, okay, will be less than epsilon. And this has to do with this series being absolutely convergent, and thus we have this result by the Cauchy criteria. Okay. So, for all n bigger than or equal to m bigger than or equal to this big N, we have, well, these are just going to be real numbers when you take the absolute value of the complex numbers, and they're going to be positive or non-negative numbers. And so the absolute value of this sum is just the sum. Will be less than epsilon. You can say less than or equal to if you want to. Okay. Now here's what we do next. What we'll do is we'll concentrate on a peak. Natural number. Now choose P such that the integers uh, 1, 2, 3, all the way up to big N are contained in the set k sub 1, k sub 2, all the way up to k sub p. Then, if if n is greater than p, little n is greater than p, the numbers, so from the original sequence that we're summing up, a sub 1, a sub 2, all the way up to a sub n, will cancel. And the difference of s sub n minus s prime sub n. So here, when we look at that difference in absolute values, that's going to be equal to, well, it's going to be the absolute value, and here's what it's going to be. It's going to be a finite, so I'm not going to get too specific with it. I'm just going to describe it in words. It's a finite sum or difference, okay, finite sum or difference of terms a sub I. And here we're going to have with I being greater than or equal to n. And what I know is that's going to be less than some sum of the a sub i's, if you will, and absolute value of that. That's bringing the absolute value within the sum. And it's less than or equal to this. And that's going to be less than epsilon. Okay, now from this, what I'm going to claim is that the limit as n goes to infinity of s of n prime, that's equal to s. Well, I'll say it's equal to the limit as n goes to infinity of s of n. And that's what we're trying to prove, so here's the claim. Okay, so here's my proof of the claim, and this will give us the result we're looking for. We're going to, first of all, note that we know that the limit as n goes to infinity of s of n exists. Okay? We'll call it s. We know that because the a sub n is converged. Okay? Okay. So we'll let epsilon be greater than 0 be given. Then, if you'll notice that s sub n prime minus s, this will be equal to, we're going to try to show that this is less than epsilon for all n's big enough. This is going to be equal to s of n prime, I'll say minus s of n plus s of n minus s inside absolute values. And that's going to be less than or equal to, by the triangle inequality, s of n prime minus s of n. Remember, s of n is just going to be the nth partial sum for our regular series, plus the absolute value of s of n minus s. So we want to make both of these guys be small enough that when I add them together, it's less than epsilon. Now, because the s of n is converted to s, there exists, I'll say, a big N element of the set of natural numbers, we're going to call that J, such that for all n bigger than or equal to big N, absolute value of s of n minus s will be less than epsilon over 4. And then by our previous work in this theorem, there exists a p element of J such that the absolute value between the difference of s of n prime minus s of n, that's going to be less than epsilon over 4 for all n bigger than or equal to p. Okay? You know, beforehand we had epsilon here in our work, but the epsilon in our work previously was just for any positive number. I'm going to pick this positive number, epsilon over 4. And then, to make sure that both things happen, we let b be the maximum between big N and p. Okay. So, for all n bigger than or equal to b, we have that the absolute value of s of n prime minus s is less than or equal to, here it will be s of n prime minus, well, we had, you know, s of n, but I could pick any n I wanted. We'll say b is my n that I'll pick, plus s of b minus, it was s, which is going to be less than epsilon over 4 plus epsilon over 4, which equals to epsilon over 2, which is less than epsilon. And so that implies the limit as n goes to infinity of s of n prime equals to s.
And that's the same thing as the limit as n goes to infinity of s sub n. So that proves the theorem. That also concludes
what we were doing out of chapter 3 at this point. So now we're going to turn to chapter 7.
And it has to do with sequences and series of functions.
And in this chapter,
we will be considering complex value functions, we're going to start off with the definition. Let's do it over here. As a definition, we're going to suppose f sub n is a sequence of functions defined on set E and suppose the sequence of numbers so this is f sub n of x and run from 1 to infinity converges for each x any, okay. Then we define f of x to be equal to the limit as n goes to infinity of f sub n of x, okay, and say that's x. That the sequence of functions f sub n converge pointwise to the function f sometimes, or our book says that f of n converge to f pointwise. Okay, so I say converge pointwise. For each x in E, I'm sorry, on f to the function f on E. Okay? Now I'd like to kind of give a more verifiable description here. It's a little bit more technical. For this definition. But in other words, we say a sequence of functions converge to the function f, okay, pointwise on the setting if for each x element of E and for each epsilon greater than 0, okay, there exists a natural number n, an n element set of natural numbers, such that for all n greater than the big N, the absolute value, so this is the complex number, of f sub n of x minus f of x will be less than epsilon. And that's our conclusion. So what we're saying is, to converge pointwise, then you give me, for the sequence, f sub n, to converge pointwise to f. That means that for each x in E, you fix an x in E, it doesn't matter which one it is, and you give me an epsilon greater than 0, we can find a spot in the sequence of functions such that from that spot on, the distance between f sub n evaluated at that particular x minus f of x will be less than epsilon. Okay? Now that spot n will depend on epsilon, and it will also depend on the x for pointwise convergence. So that's what we have. We're going to do examples of this pointwise convergence a little later. But first I'm going to write down another definition. So as a definition, suppose f sub n is a sequence of functions. Okay. Is a sequence of functions defined on a setting okay, and suppose the series is n runs from 1 to infinity of f sub n of x converge for every x in E, okay? Then we call f of x, that's right, f of x equal to the sum is n runs from 1 to infinity of f sub n of x, the sum function of the series. Sum is n runs from 1 to infinity of f sub n of x. Okay. Look, I want to say something about both of these definitions in terms of technology. It's about the function f, both of those definitions. here's what I want to say. In these two definitions, okay, F is often referred to as the limit function. Okay. Now, the main part of this chapter has to do with if f sub n's have certain characteristics, will the limit function inherit those characteristics? Let me write this down. So here's the way I'll put it. We will be concerned with discovery if properties of f sub n will be inherited by f. Let me elaborate on that just a little bit. And we'll call it quits after I elaborate. For example, if the f sub n sub x are continuous, will f be continuous? Okay? That's, will f, the limit function. Let's write it that way. Will the limit function be continuous? Okay? Here's another thing we'll ask. If f sub n are differentiable, or integrable, will the limit functions be differentiable? Or integrable. And let me just say, most of these questions deal with interchanging limits. Interchanging limit processes. Okay? And we will see through examples
through examples. That interchanging limit process often yield different results. All right, that's enough commentary and enough for this video lecture. We'll start the next lecture through doing some examples. Thank you very much.